Hello everyone. In the previous class I have explained how to solve a Legendre's linear equation, which is a first type in linear differential equation with variable coefficient. To solve a linear differential equation with variable coefficient, first we have to reduce that equation to an equation with constant coefficient by using suitable substitution. For this Legendre linear equation, so these are the standard substitution. E power of t is equal to ax plus b, then t is equal to log of ax plus b. After differentiating that, we get this result. The second type of linear differential equation with variable coefficient is Cauchy's linear equation. So this is the second type, and Cauchy's linear equation is the particular case of Legendre's equation when a is equal to 1 in this variable element, when a is equal to 1 and b is equal to 0. Cauchy's linear equation is a particular case of Legendre equation when a is equal to 1 and b is equal to 0. Here let us take the Legendre's equation as equation number 1. As I said, it is Cauchy's linear equation is a particular case of equation number 1 when a is equal to 1 and b is equal to 0. Then what is the resultant equation here? Here a naught is the constant element, that is a naught. On substituting a is equal to 1 and b is equal to 0, here the value of this variable coefficient is a value is 1 into x plus 0. 1 into x plus 0 is 1 into x plus 0 whole square, second derivative of y with respect to x. Next term a1 1 into x plus 0 y dash plus a2y is equal to phi of x. In this equation number 1, this a0, a1, a2 are constant elements, and this ax plus b whole square is the variable element. So on substituting a is equal to 1, b is equal to 0, we get this result. On simplifying this equation, a naught, here we left with x only. 1 into x is x plus 0 is x. So result in term x square y double dash plus a1 x into y dash plus a2y is equal to phi of x. So this equation is called Cauchy's linear equation. Again, here this is an equation with variable coefficient, as it represents x square, x are the variable coefficients. To solve this Cauchy's linear equation, first we have to reduce this equation to an equation with constant coefficient using suitable substitution. Similar as the previous one, that is Legendre's equation, we have to go through the same substitution by replacing a value by 1, b value by 0. Then what is the substitution here? E power of t is equal to, on substituting a is equal to 1, b is equal to 0, we left with x here. So we have to substitute e power of t is equal to x and t is equal to log x. On simplifying we get t is equal to log x in the Cauchy's linear equation. After substituting this, again this derivative values also we have to substitute. A is equal to 1, b is equal to 0. Then the value of the first derivative element is a is equal to 1, b is equal to 0. We get x into y dash is equal to a into dy. Here this capital D represent derivative with respect to t, because to reduce an equation with variable coefficient to constant coefficient, we are going through the substitution. That is, we are replacing the variable x to t. So here this is the new variable, d is equal to derivative of the variable with respect to t. So first derivative value is a is equal to 1, b is equal to 0, x into y dash is equal to, again the value of a is equal to 1, remaining element is dy. Similarly, second term a1 b0, resultant term x square y double dash is equal to a square is equal to 1 d into d minus 1 into y. Similarly, third derivative x cube y triple dash is equal to d into d minus 1 d minus 2 times of y. So these are the substitution in Cauchy's linear equation. It is a particular case of Legendre's linear equation. To solve this Cauchy's linear equation, we have to go through the substitution. E power of t is equal to x, then t is equal to log x, then first derivative with the variable coefficient, that is x y dash is equal to dy, x square y double dash is equal to d into d minus y, and similarly so on. We have to continue like this depending on the order of the derivative. So remember this, in both of the equations the degree of that variable term must be same as the order of the derivative. Here we have a second order derivative power 2, first order derivative power 1. So this is y, this is not a derivative, x power of 0. In Legendre's also the degree of a variable element must be equal to the order of the derivative. So this is the procedure to solve Cauchy's linear equation. First we have to take e power of t is equal to x, t is equal to log x, and depending on the order of the equation we have to take the derivative result, and then using the substitution we have to reduce this to equation with constant coefficient, and using the regular procedure by finding complementary function particular integral we have to solve that equation. Let us solve some problem on this. The first problem on Cauchy's linear equation is x square y double dash plus x into y dash plus y is equal to 2 times of cos square of log of x. So this is a second order Cauchy's linear equation. So first reduce this equation, which is an variable coefficient, reduce this to the constant coefficient by using the procedure. So for that consider the given equation, given that x square y double dash plus x into y dash plus y is equal to 2 times of cos square log x is the given differential equation. For Cauchy's linear equation substitutions are, we have to substitute e power of t is equal to x. If e power of t is equal to x, then t is equal to log x, and the value of x into y dash is equal to, x into y dash means first derivative value is dy. Here this capital D is derivative of a variable with respect to t, derivative of a variable with respect to t. X into y dash is equal to dy x square y double dash, that is the second order derivative is d into d minus 1 of y. So these are the substitution to reduce an equation with variable coefficient to constant coefficient in Cauchy's linear equation. So this is the common substitution for all the problem if the given equation is a Cauchy's linear equation. But in Legendre's linear equation, based on the value of a and b, we have to substitute the result. So substituting these values, equation, let us take the given equation as equation number 1. On substituting these values, equation number 1 becomes x square into y double dash. X square into y double dash is d into d minus 1 y. d into d minus 1 y plus x into y dash. X into y dash is equal to dy plus the last term y. X square y double dash plus x into y dash plus y is equal to 2 times of cos square, and the value of log x is equal to t, 2 times of cos square t. So now this is an equation which represent equation with constant coefficient. Simplifying this, y is the common term, d into d square, d into minus 1 minus d plus 1, and the common element is y. And here we have 2 times of cos square t. To find the solution of an equation with constant coefficient, we have to find the solution of the LHS part, that is complementary function, and RHS part, that is particular integral. To find particular integral, we have three types. One is an exponential equation or an exponential function. Second one, type 2, that is trigonometric function, and type 3 is a polynomial. So this comes under type 2, that is a trigonometric function. But in type 2, the function must be in the form of sine to the power of 1, sine at or cos at. But we have cos square here. So we can't apply type 2 procedure to find particular integral here. For that, we have to reduce this cos square to a trigonometric function with power 1 using trigonometric result, and we are using the result 1 plus cos 2t divided by 2. The value of cos square is 1 plus cos 2 times of the angle divided by 2. Here the value of 2 get cancelled. Here the value of minus d plus d get cancelled. Resultant term d square plus 1 of y is equal to 1 plus cos 2t. So this is the obtained equation with constant coefficient. So now let us find the solution of this by finding complementary function and particular integral. To find complementary function, auxiliary equation is m square plus 1 is equal to 0. As the derivative represent m square plus 1 is equal to 0, then m square is equal to minus 1, m is equal to square root of minus 1, which is equal to plus or minus I. The value of the obtained root is plus or minus I, which is a complex root. So for the complex root, therefore for the complex root, complementary solution is, here the real part of this complex element is 0. Yc is equal to e to the power of 0t c1 cos 1t, because 1 times of I we have, plus c2 sin t. So this is the complementary function. Later we have to replace the variable t to x. So here, that since the differential equation contains d by dt, we are writing the solution in terms of t as the independent variable. Next, to find particular integral, that is to find yp is equal to, formula is phi of t. Here we have t as a variable, phi of t divided by f of d. So the value of phi of t is 1 plus cos 2t divided by f of d value is d square plus 1. So simplifying this again, on splitting the numerator, 1 divided by d square plus 1 plus cos 2t divided by d square plus 1. 1 divided by d square plus 1 and cos 2 divided by d square plus 1. As a procedure of type 2 function, that is for a trigonometric function, we have to replace d square by the coefficient of the angle of the trigonometric function. Here we have 2, that is minus 2 square. We have to replace d square by minus 2 square. Here we have a constant term in the first element. Since we have 1, so let us write this 1 in terms of trigonometric function. That is 1 can be written as cos 0t. 1 can be written as cos 0t because cos 0 equal to 1. That is, here the value of the constant element, coefficient element is 0. We have to replace d square by minus 0 square, that is nothing but a 0 square. Therefore yp is equal to, in the numerator first element we have cos 0t, which is equal to 1, divided by the value of d square is equal to 0, 0 plus 1 plus cos 2t divided by minus 4 plus 1, which is yp is equal to 1 minus 4 plus 1 is minus cos 2t divided by 3. So this is the particular integral of the, here the obtained differential equation with constant coefficient. So therefore solution is y is equal to yc plus yp, where the value of yc is e power of 0t equal to 1, remaining c1 cos t plus c2 sin t plus yp value, that is 1 minus cos 2t divided by 3. But the given equation contains x as the independent variable. That means we have to write the solution of y in terms of x. For that, replace the value of t by x, that is t is equal to log x. Here we get y is equal to c1 cos t value is log x plus c2 sin value is sin of t value is log x plus 1 minus cos of log x whole divided by 3. So this is the complete solution of the given Cauchy's linear equation. Second problem on Cauchy's linear equation, that is x y triple dash, that is third derivative of y with respect to x plus second derivative of y is equal to 1 by x. So I have given that x y triple dash plus y double dash is equal to 1 by x. So before going to take the substitution, here observe, here we have x y triple dash plus y double dash is equal to 1 by x. For Cauchy's linear equation, the degree of the variable element must be same as the order of the derivative. Here we have third order derivative but x power of 1, but we need here x power of 3. In the second term we have second order derivative but we have a constant term, that is nothing but x power of 0. That means here we need x cube and here we need x square. To write this equation in the standard Cauchy's form, the degree of the variable element must be same as the order of the derivative. So to get that degree of that equation, multiply the complete equation by x square. On multiplying by x square into x is x cube y triple dash plus x square y double dash is equal to x square by x, and the value of x square by x is the obtained term. So now this is a Cauchy's linear equation because degree of the variable is same as the order of the derivative. So now let us take the substitution. Substitute e power of t is equal to x. On substituting e power of t is equal to x, we get t is equal to log x. We get t is equal to log x. Then the value of x into y dash, that is first derivative value is dy. X square y double dash, that is second derivative value is d of d minus 1 of y. And the value of the third derivative x cube y triple dash is equal to d of d minus 1 of d minus 2 of y. Since we have third derivative in the given problem, so we have the substitution. Let us represent this obtained Cauchy's linear equation as equation number. After writing the substitution, let us substitute all these values in equation number 1. Equation number 1 is x cube y triple dash. X cube y triple dash is d of d minus 1 d minus 2 of y plus x square y double dash. X square y double dash is d into d minus 1 y is equal to, here we have x. Here we are completely replacing the variable x to t. That means the value of x is equal to e power of t and the value of capital D is d by dt. Simplifying this again, y is the common term. Multiply these elements, d into d, d square, d into minus 1 minus d into d minus 2. I am writing this element as it is. Y is the common term plus multiplying this d square minus d of y. d square minus d of y is equal to e to the power of t. Simplifying this equation again, d square into d cube, d square into minus 2 minus 2 d square minus d into minus d square minus d into minus 2 plus 2d plus d square minus d of y is equal to e power of t. Simplifying this again, the value of plus d square minus d square get cancelled and the value of 2d minus d is equal to 1. So this equation can be written as d cube minus 2d square plus 2d minus d value is plus d of y is equal to e power of t. So this is the obtained a linear equation with constant coefficient. So now to find the solution of this, we have to find the complementary function and particular integral. To find the complementary function, auxiliary equation is m cube minus 2m square plus m is equal to 0. In this equation, m is the common element. To find the roots of m, I am taking m as common since we have a common term. Remaining m square minus 2m plus 1 equal to 0. So then equating m is equal to 0 is the first factor. M square minus 2m plus 1 is equal to 0 is the second factor. This is in the form of a square minus 2ab plus b square, where a is equal to m, b is equal to 1. This can be written as m minus 1 whole square is equal to 0. That means we have m minus 1 equal to 0, m minus 1 equal to 0, which is nothing but m is equal to 1 comma 1. So therefore obtained roots are m is equal to 0, 1, 1. In these three roots, 0 is the real and distinct root and 1 repeated twice, that means 1 is the real and coincident root. Therefore complementary function, that is yc is equal to, for the first root, c1 e to the power of 0t. For the next two roots, since the roots are coincident, c2 plus c3t into e power of 1t. This is the complementary function. Next, to find the particular integral, to find yp here, yp is equal to phi of t divided by f of d, where the value of phi of t is equal to, we have e to the power of t and f of d value is a function of the differential operator, that is d minus 2d square plus d cube minus 2d square plus d. So this is the particular integral. To find the particular integral of this equation, we have to apply the procedure of type 1, that is an exponential function. Here the coefficient of t is 1, that means we have to replace d by 1. On replacing d by 1, we get yp is equal to e power of t divided by, the value of d is equal to 1 here, substituting 1 cube minus 2 into 1 plus 1. On simplifying this, we get 1 plus 1 2, 2 minus 2 0, that is denominator value is 0 in this step. If the denominator value is 0 in particular integral, we have to continue further, that is yp is equal to, we have to multiply that independent variable to the numerator, that is t is a variable, multiply the value of t and differentiate the denominator term. Differentiating denominator, differentiation of d cube is 3 times of d square minus differentiation of d square is 2d, 2d into 2 is equal to 4d, that is minus 4d plus differentiation of d is equal to 1, 3d square minus 4d plus 1. Again replace the value of d by 1. Replacing d by 1, we get t into e power of t divided by 3 times of 1, that is 3, minus 4 times of 1, minus 4, plus 1. Again simplifying this, 3 plus 1 is equal to 4, 4 minus 4, that is 0. Here the value of the denominator term equal to 0. Then the yp is equal to, again we have to continue since the denominator value is equal to 0. Now again multiply the variable, independent variable to the numerator and differentiate the denominator. Multiplying t, we get t square e power of t divided by differentiating the denominator. D square differentiation is 2d, 2d into 3 is 6d, minus 4d differentiation is minus 4, and differentiation of a constant term is equal to 1. So now replacing d by 1. Replacing d by 1, we get t square e power of t, 6 into 1 is 6, minus 4, that is yp is equal to t square e power of t divided by 2, which is a non-zero element. Hence the obtained result is the particular integral. So therefore the final solution is y is equal to yc plus yp, where the value of yc is equal to, so here we have c1 e power of 0t, e power of 0 equal to 1, hence c1 plus c2, and this is c3, c2 plus c3 into t e to the power of 1t, that is the complementary function, and particular integral is t square e power of t divided by 2. So this is the solution in terms of t, but we have to write the solution in terms of x. Therefore y is equal to c1 plus c2 plus c3. By replacing t, the value of t is equal to log x, c3 log x into the value of e power of t is equal to x, plus again we have t square, which is equal to log x whole square, log x whole square into e power of t is equal to x divided by 2. So this is the complete solution of the given Cauchy's linear equation. In this given problem, since the degree of that variable coefficient is not equal to order of the derivative, we are multiplying the value of x square. So this is the solution of given equation. Next problem on Cauchy's linear equation is x square y double dash minus 3x y dash plus 4y is equal to 1 plus x whole square. So let us solve this by taking the substitution. So given that x square y double dash minus 3x y dash plus 4 times of y is equal to 1 plus x whole square. Here this 1 plus x whole square can be written as 1 plus x square plus 2x. By applying a plus b whole square, we can expand that result, that is x square y double dash minus 3x y dash plus 4 times of y is equal to a square plus 2ab plus b square. A square plus 2ab plus b square, that is 1 plus 2x plus x square. So now taking the substitution, let us represent this equation as equation number 1. To reduce this equation with variable coefficient to an equation with a constant coefficient, take a substitution. E power of t is equal to x, then t is equal to log x. The value of e power of t is equal to x, then t is equal to log x. By taking this substitution, the value of x into y dash is equal to d times of y, and the value of x square y double dash is equal to d into d minus 1 of y, where the value of d is equal to d by dt. So then equation number 1 becomes, substituting x square y double dash, x square y double dash is d of d minus 1 of y minus 3 times of xy dash. 3 times of xy dash is dy is plus 4 times of y is equal to, we have 1 plus 2x plus x square here, 1 plus 2 times of the value of x is equal to e power of t. E power of t plus e power of t whole square. E power of t whole square. Simplifying this, y is the common element. Remaining term is d into d square. D into minus 1, that is minus d, minus 3d plus 4 of y is equal to 1 plus 2 e power of t plus e power of 2 times of t. So this is the obtained a differential equation with constant coefficient. Simplifying this again, this can be written as d square minus 4d plus 4. D square minus 4d plus 4 of y is equal to 1 plus 2 e power of t plus e power of 2t. Consider this as equation number 2. To find the solution of this equation, that is equation with constant coefficient, we have to find complementary function and particular integral. To find the complementary function, let us find auxiliary equation. Let us write auxiliary equation, that is m square minus 4m plus 4 is equal to 0. M square minus 4m plus 4 is equal to 0, which is obtained by replacing the differential operator to a constant term. So by factorizing this, let us find the roots. Here this in the form of m square minus 2 times of 2m plus 2 square. This is in the standard result form. A square plus b square minus 2 times of a into b, that is a minus b whole square is equal to 0. That is m minus 2 equal to 0, m minus 2 equal to 0. Therefore m is equal to 2 comma 2 are the obtained roots. The roots are real and equal or real and coincident here, that is 2 comma 2. So the solution of the real and coincident root is yc is equal to c1 plus c2t, and that coincident root is 2 e to the power of 2 times of t. This is the complementary function for the obtained real and coincident root. Next, to find particular integral, that is yp. Yp is equal to phi of t divided by f of d. Here the value of phi of t is 1 plus 2 times of e power of t plus e power of 2t divided by d square minus 4d plus 4. The value of the differential operator is d square minus 4d. Here we have d square minus 4d plus 4. So here we have 3 elements in the numerator, 1 plus 2 e power of t plus e power of 2t. Splitting those elements, yp is equal to 1 divided by d square minus 4d plus 4 plus 2 e power of t divided by d square minus 4d plus 4 e power of 2t divided by d square minus 4d plus 4. Here in the numerator we have exponential function. That means we have to solve this using type 1 procedure if phi of x is a polynomial. So in the last term we have 2 as a constant term, that is constant coefficient, here 1, and here we have a constant element. That's why we can write this as e to the power of 0t. So therefore in the first term we have to replace d by 0, in the second term d by 1, in the next term d by 2. On substituting, yp is equal to, again e power of 0 equal to 1. On substituting d equal to 0, 0, 0, remaining term is 4. 1 by 4 plus 2 e power of t divided by, replacing d by 1, 1 minus 4 into 1 plus 4. In the last term e power of 2t, replacing d by 2, 2 square is 4 minus 4 into 2 is 8 plus 4. The value of plus 8 minus 8 get cancelled in the last term. Then yp is equal to 1 over 4 plus, here we have plus 4 minus 4 get cancelled, the resultant term 2 e power of t by 1. In the first term and second term we have a non-zero denominator, that means the solution of the first element is 1 by 4, second term 2 into e power of t, but in the last term we have 0 denominator, that is denominator value is equal to 0. If denominator value is equal to 0, then we have to continue the procedure by multiplying the independent variable to the numerator, that is t, and differentiating the denominator. Differentiation of d square is 2d, differentiation of minus 4d is minus 4. Now again we have to replace d by 2 here on simplifying this. Here the solution of the first two elements are completed. We need to simplify the last term only. 1 by 4 plus 2 times of e power of t, and the value of the last term is t into e power of 2t. Simplifying d is equal to 2. Again we get a 0 denominator, that is 4 minus 4, that is denominator value is equal to 0. Since the value of the denominator term is equal to 0, we have to continue one more time. 1 by 4 plus 2 e power of t. We have to multiply again the variable t to the numerator, t square e power of 2t, and the differentiation of the denominator is 2. 2d is there, differentiation of 2d is equal to 2, and this is the particular integral value. Therefore, the solution is y is equal to yc plus yp, where the value of yc is equal to c1 plus c2t into e to the power of 2t, and the value of particular integral is 1 by 4. The value of particular integral is 1 by 4 plus 2 e power of t plus t square e power of 2t divided by 2. T square e power of 2t by 2 is the solution in terms of t. This is the complete solution of the obtained differential equation with constant coefficient. But we have to write the solution of equation number 1, that is in terms of x. So that's why replace the value of t by log x, that is replace the value of t by log x in this obtained solution. Therefore y is equal to what we have, c1 plus c2t. c1 plus c2t value is log x e to the power of 2t where we have, but the value of e power of t is equal to x, and e power of 2t can be written as e power of t whole square. E power of 2t can be written as e power of t whole square, where the value of e power of t is equal to x, that is the complementary function. And to write the particular integral, first element is 1 by 4, second element is 2 e power of t, that is 2 times of x, and the last term is t square. T square is log x whole square divided by 2 into log x whole square divided by 2 into x square. So that is the complete solution of the given Cauchy's linear equation.